NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a Ph.D. is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a Ph.D. Hello everybody, so welcome to another episode of the High Impact Thesis podcast. Today's host is myself, Christopher Luanga, and
Mohammed Ibrahim.
And we have today Nandish, who's going to talk to us about his research and what exciting things he's done. So Nandish, welcome to the High Impact Thesis podcast.
Thank you so much for having me.
All right, so we're going to start this by first asking you to introduce yourself, tell us about yourself, and then we'll move on from there. So
Sure. Okay. So my name is Nandish. I'm a final year PhD student at the School of Computer Science and Engineering here at NTU. And I have been working on robust machine learning over the past 3.5, close to 4 years now. Almost about to start to write my thesis soon. So thankfully I have a thing or two to present today.
Sure.
When I started working on this topic, this was quite novel, quite new, and I did not know what the future was at the point of time. But right now it seems very exciting because in the past 4 years, this has seen tremendous enthusiasm, both in the academic sector as well as in the industry. So, hopefully, if you're listening to it, you will find it interesting. Yeah.
All right. Let's say that you meet a stranger, for example, and he asks you about what you do in general, about your research field. How would you go about describing that to him? Like in broad terms.
Right. Okay. Let me try and put my work into perspective when it comes to the overall umbrella of machine learning. I guess we've all heard of machine learning in general, and we kind of use it in tremendous number of applications that we use daily, right?
Yeah.
There are ML algorithms working on your phone, in your computers, in some parts of your cars, in industry floors, and so on and so forth, right? What has led to ML being so popular is that over the past 7-8 years, there has been increase by leaps and bounds when it comes to performance, to the point that right now we have superhuman performance by a bunch of ML algorithms. By that, I mean for certain very specific tasks, not all tasks, of course, not yet, but for very specific tasks, we have ML algorithms overperforming what humans would do at an average level, right? So we are seeing that with more and more practical applications of ML coming up, the key decision driver of the future at some point will be machine learning algorithms. Right?
I see.
We are at a point when ML adoption is growing, and that brings to our concern the idea of reliability.
Reliability,
Right?
I see.
Yeah. So we need to have a certain degree of trust in our machine learning algorithms so that we can let them decide on their own when we have actual critical tasks where if something goes wrong, the outcome could be catastrophic, right?
All right.
So, while the hope is that, for example, if you consider the use case of autonomous driving, the idea is that an autonomously driven car will be safer than a human-driven car when the system is right. But we need to get to the point to make the system right, which is not easy, of course. Right?
You want to try to unpack that a bit? What does it mean for a system to be right, and what system are we
Exactly, yeah. So that's exactly what I'm trying to come to. So when I say a system has to be right, I mean it has to be reliable. Now, reliability has multiple ways of, there are multiple ways of defining reliability. There are multiple ways of looking at it. But the way I like to address it, based on my own survey of the literature and so on, is that I sort of break it down into two key aspects. One is robustness and one is resilience, and I'll come to all of that. Before introducing the technical terms and going into all of the jargons, why do we need reliability, right? We need our systems to give us guarantees that there will not be malfunctions or errors, right? That's the primary objective here. So in order to prevent malfunctions and errors, we need to identify and categorize the different kinds of errors that can come up, and therefore provide some degree of countermeasures to all of those, so that we have a system where, number one, we are able to identify if there are any malfunctions or errors, and also have a potential solution to it.
I see.
Right?
So what type of errors are commonly encountered in
Yeah, again, right, exactly. So that's a very good question, and that's the obvious next thing that would come to our mind, right? So how do I categorize different kinds of errors? So there are two sort of axes on which the errors or malfunctions are described. Number one is whether these errors are intentional or unintentional. Yeah. And the other thing is whether they are malicious or not. Right. Now, if they are non-malicious, if the errors are non-malicious, then it's not exactly something that we should be concerned about, because there is a problem in the system, but then the system is anyway able to deal with it somehow. So it's not a particular point of concern, but when these errors are malicious, then that's a serious cause of concern. And we can have malicious malfunctions for intentional causes and unintentional causes, right? So what I work on, which is robustness, is targeted towards intentional errors or intentional malfunctions within ML algorithms, which means that I have a very well-defined attack model and an adversary setup.
But can you give us just an idea about what's the difference between an intentional and unintentional?
Right. Okay.
What's the difference?
So, for example, there are areas of ML where we look at problems like time criticality and so on and so forth, where, let's say, a decision is supposed to be made within a period of time, and if the decision is made after that period has lapsed, then no matter if the decision is correct or incorrect, it is quite inconsequent, because the time window has crossed, and therefore we will consider it as an error. That's an unintentional error. But then if I inject certain changes within the system, if I inject faults, if I try to somehow rig the system in a way so that it is making an error, then I have a more clearer attack model. I have a very specific adversary in mind, and that's what I like to call an intentional attack.
Intentional attack.
Yeah.
I see.
Wait, this is unintentional or intentional?
Intentional is when I have somebody who is in full. I'll try to rephrase that. Okay, so when there's active involvement of an adversary into injecting an attack into a system, I call that attack intentional, right? When it is not, when it is some issue with the system itself, I call it unintentional. Does that make sense?
I see.
Yes.
Okay.
So I wonder, the way that you do your work, I suppose you'll have a list of the ways in which your system can be attacked, and then you try to find solutions. You try to, I guess, pre-program solutions so that when the system is out there in the world, it would be robust to those kinds of attacks. That's
right, exactly, yeah.
Okay.
So I would like to start with a disclaimer here, is that I have looked into a lot of such problems that I tried to solve, which I thought were important. I'm not claiming exactly that this list is exhaustive, but then it kind of covers some portion of the entire spectrum of the different kinds of attacks that you can have on a machine learning system. and I have studied those. I've tried to come up with countermeasures. Of course, it's still a work in progress, because in this domain of security and privacy, what happens is that you come up with a proposal and then somebody tries to break it, because again, since the attack is intentional, there's somebody who is putting in a lot of effort to create that problem. So it is our job to sort of one-up that adversary and try to make systems which are robust against this kind of attacks.
And you mentioned something about malicious errors or something like that?
Yeah. Okay. So malicious would mean that the problem, the error that we are encountering, would have a significant detrimental consequence to the setup, the essential ML problem itself, right? If it's not malicious, then it's a trivial problem which exists, but we don't really care.
It's not a big deal. Like some problems are more consequential to the function of the system.
Sure.
All right.
So I suppose then your field is under the large umbrella of cybersecurity. You're securing.
Yeah. So this kind of is something that lies somewhere between machine learning and cybersecurity.
Okay. Can you give us some examples of, because when this introductory part of the talk, what are some examples of models that have been attacked, or so to say?
Yeah.
Something just concrete that people might have heard of, or
Sure. So again, so kind of continuing on the idea that I mentioned earlier, right? So when I talk of robustness and robustness against attacks, these attacks could be with respect to security issues of ML or privacy issues of ML. How do I make the differentiation? So whenever the attack jeopardizes the fundamental machine learning task, which could be like an image classification task, or for autonomous driving, it's typically an object detection classification kind of task, or for text, it's speech to text, text classification, text completion, and so on. These are different machine learning tasks, right? So when the attack is directed towards breaking down the fundamental ML objective itself, then I refer to that as a security problem. And when the attack tries to leak certain parts of information from the ML framework, so when the attack tries to play around with information stored within the machine learning models and try to extract IP, then that relates to the privacy issues of ML.
Okay.
Right? And for each of the two sort of branches, one's security and privacy, we have attacks related to the models, the machine learning models, which is the neural architectures. Typically neural architectures, this could be non-neural networks as well. It's more generic than just neural networks. But for most practical cases, we look at neural networks because all of these high performance ML systems typically involve neural networks, right? So the attacks could be directed towards these models or the data, the training data itself. So for example, if I consider the privacy aspect of it, right, I could try and, okay, so consider a very simple example, right? You have some state-of-the-art machine learning model that's deployed on your mobile device, on your phone, that helps your phone to unlock by looking at your face, right? I think we've all used that feature. So that model must have been trained on some data set. Now, first of all, if I can extract that model and use it as my own, then there's a problem, right? Because somebody has invested significantly on building that setup, right? So if I can just pick it up from that device and use it for my own application without authorization, then there's a problem. That's a attack which can be considered as stealing. And the other thing is, if I am mentioning these attacks because these attacks are possible. You can do that. Yeah.
So you mean, in that case, you mean someone steals the model, like the file that makes up the model, or is it really
okay,
whether it's a machine learning thing, or it's more like someone just takes the model the same way you take an MP3 file from someone?
No. It's not like that. So basically, what you do is you treat the model as a black box, and you make queries, and then there are different techniques of it. But what you can infer is, number one, the neural architecture, and number two, the parameters or the weight matrices.
Oh, you can do that, huh?
Yeah, and if you can do that, then for all practical purposes, you have the entire model to yourself.
Right.
Oh.
Right.
But how does that look like? Do you feed the model some data and look at the output to?
Okay, so for example, I'll give you a practical example, right? What you can in fact do is that, let's say you have a model and you've trained it on some data set, yeah, and you have a decent performance of that model. Now, what I can do is, let's consider this model as a black box. I will take random samples, which I assume belongs to the domain of the data set on which it was trained, and I'll study the probability distributions that come out of the end, right? So the output is essentially a probability distribution, right? And if I study that probability distribution, I can tell you whether the sample that I just fed to the model belonged to its training set or not. So if I do this often enough, I can actually get back your entire training set. I can reverse engineer your training set.
And then what is the other way? I think you were going on to mention the second thing. So the first thing is this about getting the model, and then the second thing of attacking, I think you're going to mention. Yeah.
So the other thing is in terms of security, where we have something called adversarial attacks. What are adversarial attacks? So let's say, again, a similar example. So you have like your phone opens up, unlocks with your face, right? Now what I can do is I can take the image of another person and I can make very small little changes to that image, which won't be perceptible to human vision. And then if I sort of wear a mask of that particular person's face, right, then that will fool the model that's built within your phone, and your phone will fall prey to this
attack.
To this attack, right? So typically the other most common example that's used is, let's say you have an autonomous driving setup where there's a dash cam on your car, and that's looking at the traffic feed, and it's detecting objects, and it's saying whether it's a human or it's a different kind of a traffic signal, and so on and so forth. So I can make very small structured, we call it perturbations, on a stop sign, for example, which when a human looks at will be most obviously ignored because it's so small. But then that small change is so the machine learning model that's deployed on the dashcam of the car is sensitive to that little change that's put on that image, and then it will pick it up as like anything but stop, right? And the thing is, it's not in the digital domain now, right? Because I'm creating it digitally, sure, but if I print it out and put it on a physical stop sign, it still works.
True.
Yeah? Which is the, well, so to speak, the more severely consequential aspect of this attack. And that severely jeopardizes any trust that we can have on systems that involve autonomous driving. Because if my object detection classification fails, then So for example, if somebody else unlocks your phone using a mask, that is still that still has consequences, but not to the extent of a situation where a car probably in theory can run over a person. So that has more severe impact, right? So yeah, so that's the security aspect of it, where the attack is making the actual job of the ML task fail. And the other kind of attacks in the privacy domain is where I'm trying to steal information, steal models, and so on.
So there are, I guess there's the training phase, and then there's the inference phase that I think you've spoken about, where you have the model already, and then you confuse it in some fashion. Are there also attacks in the training phase? For example, the moment I get my new phone, I need to kind of train it to see my face that I'm the owner of that phone. Can someone bring in images or have images on the phone or in some fashion so that I have trained it, but there are already somebody else's faces there in the pipeline that it sees, and then that person can unlock? Is that something that happens?
So again, these attacks can happen in different phases. It can happen during training. The adversarial attack that I mentioned of is something that happens at inference. Now, typically having an attack during training is more difficult because training happens in a more secure environment. Right? You have more control over the system where you're training stuff. But then when you are deploying it in public, it has to be more open. It cannot be like when a model is deployed in public, for example, in a car or whatever, right? You're not anymore in the safe space of a lab where you're training your model. You can have more control over the training aspect of it. There are attacks like data poisoning and so on, which can fool the model, can mess up with the performance of the model during training. But then stopping those attacks is comparatively easier, because if you sandbox the setup where you're training your model, you're in a good space. But then you cannot sandbox every dash cam of every car. So inference is something that happens in the public domain, in that space. So physically imposing barriers to prevent attacks is harder. So therefore, defenses must be algorithmic. Does that make sense?
Yeah.
Okay. I guess I'm still a little confused about whether it's harder on the one front and the other, because the moment the model is on my phone, then it's in the public, right? But it needs to be trained. So you're saying that it's still harder to fool it at the training phase?
Okay,
because
so
they don't really have as much control once it's on my phone.
Okay, yeah, sure, very good question. So when you are training your phone to unlock with your face, that's not the full training of the setup. The phone already has a high-performing neural network that has been trained on many images, and that does its job anyway. What you're doing is you are sort of fine-tuning it for your own personal application. So you're just sort of probably making 5 to 10% of the training on your device with your own input. The rest is already done. The rest is already something that comes from the manufacturer. Because like if you are taking just a few images and training a model, the model is more sophisticated than that, and it would definitely need more data to train, and it cannot train locally. When the manufacturer is training the model, they have more control over the settings. But then the moment it goes out to the public domain, you have lesser control, and therefore the approaches to the solutions must be incorporated within the algorithm itself and should not come from the exterior.
Okay, so I think this is quite a good intro, I think, for its intro, but also I think you've gotten a little bit into what you do.
Mm-hmm.
Now we want to know what angle you're approaching it from. Yes, more specifically
Mm-hmm.
for someone who was reading a paper, for example.
Yeah.
What is it that you personally do in order to solve the problems that you've outlined now?
Yeah. Okay. So again, let me take an example and try to sort of delve a little deeper into some of the solution approaches that we've tried so far. So adversarial attacks, right?
Yeah.
Is what I mentioned. So you have these structured perturbations within text or images that are imperceptible to human annotators.
Yeah.
But any trained machine learning model is sensitive to these kind of changes within the test samples. And therefore, we have a situation where a misclassification or a failure of the ML task takes place, right? So we have, like, if you look into the literature of this, there are multiple different types of attacks and some ad hoc defenses that are proposed and so on and so forth. So we studied that to some degree, and then we sort of decided to take a step back from this cat and mouse chase of attacks and defenses, and we wanted to look into explainability. We wanted to understand why these attacks happen in the first place, and as a result of that conversation, we kind of landed at something called dimensionality, which is to do with the high dimensional nature of the optimization landscape where the neural network operates. So we tried to relate the nature and properties of the high dimensional space to adversarial attacks. And we try to understand how high dimensionality facilitates the creation of adversarial samples.
So when you say high dimensional, you're talking about the image or the high dimensionality of the model itself? What are we?
Okay, so when we are looking at dimensionality, we are looking at the dimensionality of the optimization landscape where the neural network tries to optimize.
Okay.
Which comprises of essentially all the parameters that are stored within the network.
Okay.
Right? And that's a very high dimensional space.
The parameters, the hyperparameters, anything that you tweak to create the model?
Typically the parameters themselves, not the hyperparameters. Hyperparameters are kind of external to the system. So we every time I tweak some of the hyperparameters, it's a new setup in my view. So when I'm changing, when I'm changing a hyperparameter, I'm trying to solve a new problem essentially. But when I'm tuning, when I'm optimizing within a specific problem, I'm in a very high dimensional space. So what happens here is this, that you have all of these points, all of these data points, training samples residing in that high dimensional space, and you have a hyperplane classifier that splits that space into the trained manifolds, essentially. So you have all of these regions belonging to each of the classes, and you have a hyperplane in between that splits it into all of those regions. And this is too high a dimension to visualize, but the idea is still the same, right? If in a 2D setup, if you have a bunch of points and if you can sort of draw a line or a curve that splits the points into two different regions, imagine that in a high dimensional setting, that's all. Right? But then what would happen in that high dimensional setting is very interesting. And this sort of comes from the mathematics that goes behind all of this, which is that there are a lot of quite counterintuitive properties of the high dimensional space.
Okay.
For example, if you look at all of those regions within, so if you look at the trained manifolds, it is possible to prove that most of the points, the data points, lie on the edge or the surface of those regions. So when you have a high dimensional, so when you have lots of points, okay, I'll rephrase that. So when you have a distribution of points in a high dimensional setting, it's not Gaussian at all. In a Gaussian setup, most points are towards the center, right? But in a high dimensional setting, it's just the opposite. Most points are away from the center and towards the edges.
Okay, the edges of the manifold.
Right. So what happens is that if the points are near the edges of the manifold, if I introduce a small change into one of those samples, it is easy for the sample to cross over from one side of the hyperplane to the other.
I see what you mean,
And therefore sort of change between the two manifolds, which are the two classes. And that sort of results into the creation of the adversarial sample.
Makes it easy to create an adversarial sample because it will already be very close to the other side.
Right. Had it been very far off from the edge, the amount of perturbation that you would have to do to the sample to bring it onto the other manifold would have been very high. And then that would be visible, that would be picked up by the human annotator.
Right.
But in this case, that's not the situation because the samples are anyway tantalizingly close to the hyperplane.
Okay. That's a big word, but okay.
Yeah.
Okay, so I think I get I get what you mean. Okay, so these are things that you guys found by doing math, is it? How do you come?
Okay, so the approach that we kind of take here is that. So of course I did not do the math from scratch.
Yeah.
So there is a decent amount of literature when it comes to understanding or characterizing the high dimensional space. We sort of modeled it towards our own use case of machine learning models.
Right.
That's number one. And the other thing is we looked at the exact same thing from the experimental point of view, which is we tried. So we had some results which follow the math, and then experimentally we tried to verify whether these hold good in practice or not. So we have some mathematical foundation that points to this phenomenon being possible, and then empirically we verify that it indeed does happen so for our use case, which is images and adversarial attacks on images.
Okay.
And we do a nice control experiment on images with varying dimensionality and models and so on. And the results tend to sort of corroborate the mathematical basis that suggests that this is a possibility.
Okay.
Yeah. So that was a key finding that we ended up. And we sort of made the proposition that adversarial attacks are facilitated by the presence of these sample data points in that high dimensional space. And if that is the case, then we can use dimension reduction as a potential solution to the problem.
So that would be reducing the dimension of the model? That would make the model smaller? What does it mean actually?
Okay, right. So what happens here is that we are concerned about the inherent dimensionality of the problem itself. So keeping the model same, what we did was that we used dimension reduction techniques like SVD and t-SNE and so on, right, that reduce dimensionality. And then we used those samples and checked what's the change in performance. The key thing to note here is that we also did a downscaling and a downsampling to compare and contrast with the sort of notional dimensionality of the samples versus the actual dimensionality in terms of information content.
Yeah, maybe say that one more time.
Okay, so when I say dimension reduction, it's not downsampling of the samples, the images, right?
Right.
So we did that comparison with downsampling of the test samples versus the dimension reduction using SVD, that approach to the samples. And we realized that when we do a downsampling, it has almost no impact.
Okay.
But when we do a dimension reduction in terms of information content, then we do have an impact on how the adversarial behavior changes. And we realize that if we feed a reduced dimensional sample to the classifier, then it is less likely to fall prey to adversarial samples.
So let me try to get what you're trying to say. So originally you had this very high dimensional input, then you reduce the output so that it's in lower dimensional space, then you feed that to your classifier.
Yeah.
And that, for you guys, you found out that makes it harder for someone to fool the model, or?
Yeah. So basically, okay. So think about it like this, right? So so what is the practical use case? The practical use case is that you have a dash cam in a car that's looking at images on the street.
Yeah.
And it is supposed to make a decision on the fly. Now, what are the things that I cannot change? I do not have any control over the actual physical thing which exists. So I cannot go and change the stop sign and sort of get rid of the adversarial perturbation. I cannot do that, right? Neither can I change my actual model because that's already there in the dash cam.
Right.
So what I do is I add a block that sits between, let's say, the camera feed and the decision-making setup that reduces dimension of the images that are being picked up by the camera. And if I do that, then even if the camera picks up images of adversarial samples from the outside world, those samples after dimension reduction will have gotten rid of the adversarial perturbation to an extent such that the decision-making setup will no longer make the error that it was making earlier.
I see. So you would have to make significant changes for it to be picked up, in other words.
Right, yeah. So in that case, for example, the amount of change that I would need to make to the stop sign would make it so different that it's no longer a stop sign anyway. Right?
Okay.
For example, if I paint the stop sign green, then that's not a stop sign anymore, right? So our goal is to ensure that we can have a setup where the amount of perturbation that is needed to create the adversarial sample is high enough to be picked up by human annotators.
So in the case where the model has been deployed, it's there out there, the human is not able to actually see. So how do you, I guess, if the model has been deployed and indeed there is a change that is so obvious, does the human come in, or it's never, so they can't really do anything about it?
Right. So for example, if I paint a stop sign green, then a human driver would also spot it.
Right.
And let's say a pedestrian who's walking will also see it as a green sign and will not sort of try to cross the road from there because the pedestrian also sees that as a green sign for the car. Do you know what I mean?
Okay, maybe I'm not clear about the deploy. How do you then use your innovation in the deployment setting?
What I do is I add a block within the pipeline that does the processing in the car.
Okay.
Where I have, so what did we have earlier? We had a camera and a decision-making setup.
Yes, you get it from the camera, you put it into the decision-making thing.
Right? Yeah. And the decision-making setup was making an error in judgment when the camera was feeding to it some samples which were of adversarial nature, right? Now, if I put in a block there that does dimension reduction, then in the process of dimension reduction, the adversarial noise is lost, and we have practical evidence of it. And therefore, when the processed samples are fed to that decision-making setup, it is not falling prey to the attack which has been provided to this car from the exterior world.
Okay. So the attacker would have to send in... How would the attack be carried out if I were to say... Suppose there is the model without your solution right now. How would I attack? Would I change...
I would just add very small changes on the stop sign on the side of the road.
So you mean in the physical world? The changes made in the physical world and the camera picked them up?
Yeah, absolutely.
Or is there a way for someone to also change in the the camera itself? I guess it sends the image to somewhere, right?
Right. So if the software within the camera is jeopardized, and if you are able to inject attacks on the images after the camera has picked up the images, that's also possible.
Right.
That is also taken care of by the block that sits in between the camera and the decision-making setup.
I see.
Now, the next question is, what if I tamper with the decision-making setup itself? That is also possible, right?
So that was what you were talking about earlier about...
That's the other aspect. Right?
What do you do about that?
Yeah, so then we can have certain guarantees on checking whether the decision-making setup is intact or not. We have some verification protocols that run from time to time. And we use things like watermarking.
Okay.
And I will come to that a little later because that's also something that we've worked on. That kind of... That is the aim of all that work, is to ensure the integrity of the models that are being deployed.
Okay.
Yeah. So what I was talking about in terms of adversarial attacks and defenses using dimensionality, we've tested this on images, we've tested this on text classifiers, we've tested this on video streams, as in object detector and classification, that sort of a pipeline. And it works quite uniformly across the board.
Okay.
Yeah. This is the work that we've been doing in terms of security of ML. And when it comes to privacy, we've looked at two things. Number one is the privacy of the model, which is the neural architecture, the trained model. And the other thing is data privacy. I'll come to that a little later because probably that's kind of unrelated to what I've been talking of so far in terms of the use case of the car. Right. So, for example, consider this. So, let's say you've developed an algorithm that does the decision making after the feed comes in from the dash cam of the car. Now, two things. Number one is that you've invested a lot in training that model, so you would want ownership of it. So that another car company is not able to take your model and use it without authorization.
Let me just, before you continue, do you think there is a potential future where the government can just provide these trained models? Because if everybody has the best of the best, then it's safe for the whole world, right?
Yeah, in fact, that's a very interesting point because Singapore is one of the first countries where we have there's talk of building a framework for AI security and privacy. I don't think it's out yet. There is a framework on AI ethics, which is a different topic. But then I think there is a lot of discussion about coming up with protocols and standards and so on that ensure that we have a certain degree of security and privacy for the machine learning models that we use. Now, for the government to get involved, there would be a requirement of a lot of standardizations to take place, right? And this has to be a public-private sort of collaboration situation, right?
Okay.
It cannot be strictly government. But then it's a nice initiative if it is done, because it's needed. It's definitely needed. So regarding the other kind of work that I have been working on, which is ensuring that if you're investing in developing a model that does the processing behind your dashcam, then you have ownership of it. So what we did is we looked at potential different ways of doing it. And one thing that we landed up on was watermarking neural networks. Watermarking neural networks existed as a field of study with certain flaws where you can actually steal the model by making small changes. So what we did as part of my research is that we set up a goal where if you have to steal a model from my trained model, then you will have to retrain all of the layers of the model, which is in a sense as good as training a fresh model. Right? If you can retrain all of the layers of the model, then you can train a network from scratch. You don't need to steal it anyway. Right? So that being the goal, what we did was we were able to map watermarks or embed watermarks within the neural network by using something called backdoors.
Okay.
So what are backdoors? Backdoors are specifically just like you consider a regular neural network which has all of these trained weight matrices. I can modify a few of the weights within those matrices such that those weights are sensitive to a very specific set of inputs.
Okay.
And the model works properly for all other generic inputs, but works differently for those specific set of inputs. And we call those inputs trigger samples.
Okay.
So those trigger samples trigger a different behavior for the network. Right? So what we did was we tried to sort of model, have this idea where these trigger samples is my private key.
Okay.
And that resides with me. And this model behaves differently for those trigger samples. So if I have that private key, and if I can show in public that for my specific set of samples, the model behaves differently, but for all other samples, it works in the standard way, then that can be used as a way of verification.
Like your signature.
Yeah,
Like
that's
your fingerprint.
That's my fingerprint. That's my signature. Yeah, exactly.
Okay. So let me just try to understand a bit physically how this works, because once I give you a model, it's in a format that's public, like .h5 or something. So you guys, if I read your data, if I read your model on my computer, you mean I would get wrong results just because I don't have these 5 or so images that
No.
How does it physically work?
No. So let's say you have a neural architecture with all the trained weight matrices.
Right.
I am using it with authorization, right? Because I created it.
Right.
Now you have stolen it.
No, let's say Muhammad has stolen it.
Okay, sure.
I don't like stealing.
Sure. So let's say you have stolen it and you are using it. You are still getting all the good results. That's fine. But then the moment I realize that somebody else is using it, what I'll do is I will say that, okay, let me put this model to test. And this is what we call verification, right? So I will have a set of samples with me, which when fed to the model will work, the model will work in a different way. And if I can show that the model behaves in this specific way upon the introduction of the samples that I have, but you do not have, then that can be used as a means of verifying my ownership of the model, and the rest is legal.
I see. Okay.
Okay.
The rest is legal.
So it's one way to verify the integrity of the system.
Right.
No. I think it's one way to verify ownership.
Ownership, not
Yeah.
So I go to a court and I say, look, here is a few set of samples. I can show you that it's working differently, and this person cannot show you. Then the court says, yeah, actually, because he had to pre-program it, right? Internally. To say, once you see these, you behave in this way. So it can only be me. I see. That's pretty cool.
Interesting. Yeah.
Okay.
Yeah. So that's work that we have done. Again, we have tested it on images and text. And incidentally, we gave it. This we are currently in the process of patenting this technology, right? And so we had to give it a name. So since it's robust watermarking using backdooring, we named it Roback. And then we tested it on text samples, and it also works for text.
Okay.
So we call that text back.
Okay.
Yeah, and it's just for fun.
Okay.
And so that's one way of addressing the issue of privacy for the model, where the attacker tries to steal the model. So as I said, we always have an attack model, an attack feature. There is an adversary that is trying to carry out an attack, right? In the earlier case, it was the fact that the adversary is making small changes in the samples. Here, the adversary is trying to steal the model. And there's another aspect which comes up from the idea of distributed learning, where we have sabotaging attacks, and I'll just quickly spend a bit of time on that to wrap up the work that we've done so far. And for that, let me take another use case. So I've talked about use cases involving your phones, your dash cams of a car, autonomous driving. So let's talk about healthcare. Where we have a lot of new developments coming up in terms of ML adoption. Right? So let's say you are a hospital and you have patients who have their MRI scans, and you have developed a system, a machine learning model that looks at the MRI scans and is able to tell you whether you have a disease or not.
Yeah.
It's a very standard machine learning problem.
Yeah.
Now, when I look at this particular data, there are two things. Number one is that this data is expensive. Getting an MRI scan is not cheap. Number one. And number two is that this data belongs to a specific person. So it's extremely sensitive. And this cannot be shared in the public domain. Right? Now, there are multiple hospitals in Singapore or any region, and they all have their own set of patients, and they can all develop their own models which are trained on their locally available data. So they have some degree of accuracy for each of these models. But if I can have a system where all this data can be pooled into one central data repository, and then if I can train a model on that, that model is very likely to outperform any of these individual models. Because more data, the better. Right?
Okay.
But then that's not possible because of the sensitive nature of the data and the cost that's incurred in curating this data set that resides with the individual players. Right?
Right.
So what do? You have to have a setup where you can accumulate the insights without sharing the data. So we do this by a technique called federated learning.
Okay.
What happens is that you have a central server which creates a very basic generic version of a model, essentially creates the neural architecture and sends it to, let's say, all of the hospitals. And each of these hospitals, they retrain the model with their own data and they push the model back to the server. And the server aggregates all of those models at the model level, not the data level. And that's possible. So when you aggregate the models at the model level and create a federated model, that definitely outperforms any of the individual models. Right? This is the idea of federated learning. This is a very standard distributed machine learning framework. Now, what is the attack kind of situation that fits to this paradigm? So in this case, for this to work, you have to have a situation where all of these players, for example, the hospitals, cooperate. What if I have one of those hospitals who is a bad guy and who intentionally pushes a bad model to the server so that the overall performance comes down? That's possible?
Yeah.
Right? Also, what is the guarantee that the server itself is not compromised? So then we have multiple modes of attacks possible on this framework. And what we are trying to do in terms of the attack itself is that the attacker, the adversary, is trying to leak the data, right? Or spoil the performance of the model. So what we did as a countermeasure to this is that two things. Number one is that when these individual hospitals or individual players are sending a model to the server has a data set that resides locally with it, which the server refreshes over time. And the server uses that data set as a validation data set for the model that you've sent. And based on the performance of your sent model on the server's own data set, you will be assigned a weight. So if you push in a very poor quality model that is likely to perform very poorly on that locally residing data set, then the associated weight will be less.
Okay, so the very high performing models would get more, I guess, will have more of an impact on the federated model that you finally end up with.
Precisely, yes.
Okay.
Yeah, so that way it works. Just flip the situation and think that what if the server is compromised?
Right.
So if the server sends a poor quality model to one of those clients, the clients anyway have their local data, right? So they use that local data or a part of the local data for validation. And if the performance at the time of the model that's sent by the server is lower than the performance that it has locally, then that model is rejected.
Right. So if I am the hospital, then I check that the federated model is not as great as my own local model. I just ignore the federated model.
Right.
Okay.
Right.
Makes sense.
That way I have a situation where my locally performing setup is not anyway worse than what would have happened if I would be playing independently.
Right.
And for having that checks and balances situation with the server, with the weighted sort of federated averaging setup, I'm ensuring that I am prioritizing those models which are high performing. So that number one is that it provides the setup for having the best performance out of the given models. And number two is that it takes care of any sabotaging attacks, right? So this is what we called a robust federated learning setup. And again, we came up with a funny name to make it funny. We called it Robust FL, ROFL.
Yeah.
Sorry, Robust FL?
Federated learning.
Okay.
Yeah, so ROFL.
Okay.
Yeah, so the idea is essentially that we have these validation checks at the server level and also at the individual client level, so that we stand to benefit from like the other players who are willing to improve the performance of the global model.
Okay. So I guess on a very large scale, if you have thousands of hospitals, it's great. I'm just wondering, I realize you use the hospital as one example of a higher level. Many systems could fall under that. But for specifically the hospital, wouldn't it be fine to just send the images and anonymize them, not really tie them to a specific person?
Okay, so when it comes to the anonymizing thing, the masking thing works for use cases which are not related to healthcare. For example, federated learning in the first place was developed for one of the primary use cases was your Google keypad, the Gboard, right?
Yeah.
So the typing thing, the swipe to type feature was developed as part of this, where your private data was not sent, but then it was kind of anonymized and then sent. Now, the sensitivity of your typing pattern is alright, you wouldn't mind too much. But the sensitivity of your MRI scan is of the highest level. So when it comes to healthcare data, there is like that's the number one priority in terms of privacy. So in a practical scenario, almost nobody will be willing to share their data with people who they do not necessarily trust.
Okay.
All right. I guess now we can zoom out a little bit from the details and perhaps ask broader questions about the field in general and where it's heading. So I have a couple of questions here for you. So the first one is, so are these challenges with security and so on, are they like global across the board for all applications of machine learning, or are they more specific to certain areas? Do we face the same challenges in all of them, or?
Yeah, so these challenges are agnostic to the specific use case, but we use the use cases to substantiate the results that we want to find. For example, adversarial attacks can happen in image classification, it can happen in object detection, it can happen in text classification, text completion, speech to text, almost all of the areas where machine learning models are typically used. But then when we are studying them, we kind of study them under the umbrella of one of these applications for easier comparisons and so on and so forth.
Sure.
But then when you put together all of the results that you find in all of these domains separately, then you get the idea that, okay, so this is something which is actually generic to machine learning itself, and therefore the solutions should also be something which can be mapped to any domain as needed.
So once you develop a certain solution, it can be more easily applied to others as well.
Right. Sure.
All right. Also, another question I had is regarding what kind of standards or threshold for that we need to reach before we say, okay, the system is okay, it's quite secure, let's put it in the public domain?
Yeah, that's a very, very good question. And that's kind of what we were talking about a little earlier regarding standardization of security guarantees and the government getting involved and so on and so forth.
Mm-hmm.
For example, in typical cryptography and in its applications, there are globally accepted IEEE standards that define that, okay, if these properties are met, then this can be used as a tool. For example, a cipher and so on and so forth, right? Because we have a good understanding of the amount of computation prowess that is needed to break a cipher, and since that's most likely not possible with classical computing, therefore this cipher works. So for the domain of cybersecurity in ML, since it's new, we do not have that definition of what is the extent to which the machine learning model should work without any errors in order for us to consider it as something that's trustworthy.
I see.
So that's again a very, very interesting field that needs to be studied. It will come out as a direct consequence of the research that we are doing and the entire community involved in this domain is doing. But then that certification, that kind of standardization across the board, and this has to be a global effort, because most of the ML tools that we use are not geographically limited, right? So this has to be a very serious effort that I'm sure will be done very soon as more and more ML adoption happens. Because see, 4 or 5 years back, ML was an added advantage to your company's portfolio, right? A company would say that, okay, I'm using ML to do something nice. And now it's 4 years down the line in 2022, it's kind of a basic fact that there is some ML application in your portfolio, whatever you're doing. There is some aspect of ML that's being used.
Yeah.
So as and when this becomes more universally used, the regulations should come in, and I'm sure they will.
All right. And also another question I had is, do you think all of the solutions that people are coming up to deal with these challenges, are they all aligned within the same, are they all along the same lines, or are they more diversified in terms of approaches to solve these issues?
I think there's a huge diversity in the approaches people use, which is a good thing.
Yeah.
Because you have the option of playing around with a multiple variety of solutions that you can choose from. So that's nice.
Yeah.
But then that also brings in the problem as to how do you understand which is the best solution that serves your purpose without exactly specifically knowing what your purpose is. Because, I mean, not necessarily everybody who uses ML is an ML expert. Right?
True.
And that's why I think we need this kind of certifications, right? So that a person who is not an ML expert will just look at the certification and will know that, okay, so this guarantees me a certain level of security and privacy, and I have my own requirement of security and privacy based on a security and privacy audit of my company or of the offerings of my company. And if the needs, if the requirements are met, then I'm good to go. Right? So I think a standardization protocol is necessary in that sense.
Is there research going on that would make it part of the model, this whole security apparatus you're talking about, as well as So instead of having a certificate, when I get a model, for example, I can just, I don't like check some kind of thing, right? Like I look at it and I know that it's got a problem or it was trained properly. Like, is there a way to encode the history of training in the model itself, so that once someone gets it, they could be anywhere in the world, they can verify or they can check how it was trained. Are there?
Yeah. So there are ways of doing that. For example, the watermarking that I mentioned, right? That's something that can be sort of verified as and when required, right? Okay. But then the idea of having a certification is that it transcends the ML community, and therefore it makes people from other domains who are just users of ML and not necessarily people involved in the development of ML.
I see.
They can benefit hugely from that effort.
I see. That's good. So as we move toward the end of the conversation, we'd like to talk about you, the person, and hear more about what you do when you're not doing your research. Music you play, the dances you dance to, all those kind of stuff. So what kind of person are you outside the lab?
Very interesting. Let me see. I mean, right now I'm in my final year, so barely outside the lab these days, unfortunately.
Surprising.
I mean, I'm sure you know exactly what I mean. You've been through that as well. But okay, so what kind of a person am I? Let me think. I guess when I'm not working, I am extremely interested in stories, as in the art of storytelling and listening to stories or looking at stories. So I inherently try to find a story in everything that I do, right? So if I'm watching a film or I'm reading a paper, whatever I'm doing, I'm trying to, in my mind, involuntarily looking for some story that I can relate to. Yeah. And I'm like, I mean, I used to write a lot back in the day. When I was in college, in fact, a group of friends and myself, we made a film in our own vernacular language that's on YouTube. In fact, when I saw this studio, right, and I saw these sound proofing panels, that's the first thought that came to my mind, because back in the day, what we were doing is, so we didn't have any money, right? Yeah. We did not have a producer. So, and we needed to hire a studio for the music and the voice dubbing and so on. And we could not rent a professional studio. So we had this bunch of friends who now they are proper musicians, but back in the day they were just starting out and they were building a studio. So the deal was that we'll help you set up the studio. We'll build, we'll put the manual labor to create the soundproofing systems and set up everything. And as a return of favor, you will let us use your studio for a week so that we can record the music and so on. So yeah, that was a nice experience.
And what kind of music you're playing?
So I do not play any music, but in the film we had a synthesizer. The drums were, I think it was made in a computer. I think it's called Additive Drums. So we had a digital audio workstation and we pulled in the drums from there. But the synthesizer and the guitar were performed by actual people.
Live, yeah.
Yeah, so yeah, that was a nice experience. And recently, in fact, so NTU, GSA, and I think this is School of Humanities, they had a short story writing competition a few days.
Yeah, I think I've seen that, yeah.
Yeah. So I sent a story and I won that. So I got the first prize.
Oh, nice.
So
congratulations.
Yeah, thanks. I mean, that was fun. But the sad part of that is that I wrote that story about 10 years back, and I just repurposed it for. So they allowed any submission which is your own and not published, right? So this work sort of ticked both of those boxes. It was my own, definitely, and it was not published because I have like a diary full of those writings. So I just typed it out and sent it to them, and yeah, it worked. So
Nice.
that was nice, yeah. And other than that, I mean, right now I'm a little more stressed than I should be because I have to submit my thesis in about 4 months. July. Yeah.
Well, wish you all the best. I think almost all of us here.
All of us, yeah.
Yeah.
Well, he already did, but we are in the same boat.
Yeah. Hopefully we all get there with flying colors. Good luck to us. Yeah.
Yeah.
All right.
Any other thing that you wanna talk about or mention? Something that we've not been able to ask? Something you want to clarify that we asked? This is your time.
I mean, I think first of all, I would like to thank you guys for this initiative. I think it's brilliant.
Thanks.
I mean, it's a nice space for discussion that's there. But the other thing is that, I mean, what I would expect is that once this goes out and other people listen to this recording, if there are others who are also interested in the topic who can maybe reach out and have collaborations, I think that would be brilliant. Yeah. Because we often do not get the space to interact with people who are not necessarily working in the same group. So, I mean, the collaboration is there, but it's quite myopic in my sense, in my ideas. So if this is a platform to reach out to others for sharing their ideas, brainstorming, coming up with new ideas, and so on and so forth, that would be very nice. And so I think this is a very nice initiative by you guys. So that's very well done. And of course, thanks a lot for inviting me and letting me share my 2 cents on the work that I've been doing so far. Yeah,
All right,
appreciate it.
Sure.
Thank you for coming.
Thank you very much.
And I think the folks who are listening, we will in the future have an email where you can. Is there a way for people to reach us on the podcast platform?
Yeah.
Okay, so on the podcast platform, you can just contact us. If something is interesting that our guest said today that you'd like to follow up on, just send us an email. But you can also look, I mean, not just today, for any of the other recordings that are on this podcast. We welcome your feedback. If you'd like to collaborate, Nandish here and all of our other guests would very much like to do that. So Nandish, we appreciate your sharing today. We learned a lot. The things that we've learned today is, we'll just try to quickly summarize, the things that we've learned. Machine learning is a complex field, but you're trying to make it so that folks outside can also understand. For example, someone who doesn't really have any background in machine learning, they can just look at a certificate and say, oh, this was done properly, for example. You're also working on making sure that it's reliable. That's the most important thing, right? So once it's deployed, you're not done yet. People can still attack it and so on. And your work is really focusing on ensuring that your model, even after it's in someone's hands, is still robust enough to make sure it doesn't get attacked. So this is really great work. I believe that applications will be very broader than the things you've talked to us about today. So we really enjoyed the conversation. And we know that this will have a very high impact in the world.
Thank you.
Thank you, everybody. Bye-bye for now.